In our first example, finding confidence intervals, what we're going to do is we're going to take our data from above. That's the data analyst starting salary data. And this is what we're going to do. We're going to try and find a 95% confidence interval and a 99% confidence interval. And we'll figure out how those two are related. And we're going to use the data that we had up above, which was the 10 starting salaries for just a sample of 10 data analyst positions in the Midwest. We're going to assume that we know the population's standard deviation, which most of the time we don't, but let's just assume for now that we do. And then let's talk about how can we find a 95% confidence interval. So remember that that's the interval that will contain the mean of 95% of the samples of size. In our case, we're talking about samples of size 10 because that's how big our sample is. So that's what we're going to do. We're going to try and find what's the interval that will contain the mean of 95% of the samples. And then we need to figure out how do we do that? How do we figure that out? And so what we're going to do is, I told you up above, kind of inexplicably, that the confidence level is going to be denoted by 1 minus alpha. And the alpha value has a name, and that's called the significance, and we'll talk about that in the next chapter. Don't worry about that for now, but 1 minus alpha is the confidence level. And so if we're talking about a 95% confidence interval, I'll call that a CI, that means that 1 minus alpha is 95% or 0.95, and therefore alpha is 5% or 0.05. Okay, so we're going to take alpha to be 0.05. And what we're going to do is we're going to think back, and we have to combine the two facts that we saw before from chapter 6 and chapter 7. We know that, this picture is actually helpful, we know that our x value is going to be the mean, which we're assuming is our sample mean x. We're assuming that those are the same, plus our cutoff point, which I'll explain what that is in a second, z, times our standard deviation, which we said was sigma over square root of n. Now the z value, the z cutoff, what that's going to be is, that's going to be the cutoff. We want to figure out what is this cutoff so that the area to the right, the area under the curve to the right of that cutoff is alpha over 2, because we want, for a confidence interval, we're going to have two sides to it. So it's going to go from one value to the next, and we can either be off by being below the confidence interval or above it. And so this is going to be the cutoff, z sub alpha over 2. Now, because this value, there's a symmetry here, this is minus z sub alpha over 2. So really, this is going to be plus or minus z sub alpha over 2. So it's a very hand-wavy introduction to the formula, but that really just involves knowing a few things. That involves knowing the formula for the standardized variable and solving for x. Okay, so that's the unstandardized variable. And then knowing, remember that the notation z sub alpha over 2 is exactly this. What's the cutoff so that the area under the curve is alpha over 2. And then the standard deviation of our sample, the standard deviation of the set of all sample means, I should say, is the standard deviation of the underlying population divided by square root of n, as we talked about in chapter 7. Okay, so putting all those facts together, this turns out to give us our confidence interval. And so knowing that is enough for us to compute the confidence interval for a 95% and then a 99% confidence interval. And so let's do this. We've already done actually a lot of the work. We know that our n, we know that our n is 10, because we have a sample of size 10. In general, lowercase n is used to describe the sample size. We're assuming, based on the problem, that the population standard deviation is 4. And then we computed that if we take the sample mean of all the data that we have, that was 63.54. Okay, so we did that above in the previous example. Now, if alpha is 0.05, we need to figure out what is z sub alpha over 2. Okay, so this is z sub 0.025. And there's a few different ways to do this. The first way to do this is that this is on the handout for the this is on the handout for all the formulas that we have. And so I'm going to pull up the handouts here. Okay, so let me show you that. Okay, so you should be able to see the handouts now. And so we're going to jump down to chapter 8. Okay, and so yeah, this is the standardized version. This is what we were just talking about. This is really the flip side of what we did before. We had it solve for x. But this is the confidence interval formula that we just derived. We'll talk about the other stuff later. But the other thing I wanted to show you here is that at the bottom where there's a table, what we have are these values. Okay, this is kind of hard to find, which is why I wanted to show you together. But we have these values down here. Let me try and zoom in here a little better. So we have these values. And so we're looking at our cutoffs, and we were looking at the value z sub 0.025. And so that's 1.96. Okay, but that table there is exactly the table that we're going to use to get the cutoffs for this problem. This table is on the page that's after the normal distribution table that we had already talked about. Okay, so this is after that. We will talk about this table soon. Okay, so we will talk about this table actually in the next video, but that's where that's where those values are. All right, so let's jump back to the iPad. Let's talk about how do we figure out what the confidence interval is. And there we go. So we want to talk about how do we find the confidence interval. Well, at this point, we know all the values. We can just plug everything in. And it turns out that what we're going to do is we're going to end up with our mean was 63.54 plus or minus this other stuff, which was 1.96 times 4 over square root of 10. And so what we have to do is plug all this into a calculator. I'm in the habit now of just using R as a calculator. So we're going to plug this in. Try this on your own. Don't trust what I'm going to say. But what we're going to do, and let me show you how I'm going to do this using R, because this is slightly different than, there's a few different ways to do it. But what I'm going to do is I'm going to compute that value 1.96 times 4 divided by square root of 10. Okay, and so that's going to be the value that I'm going to call E. E is going to stand for our error. And our error happens to be 2.48 roughly. And so what we had before was we had our mean, let's call it M. And there's a few different ways to do this. I'm tempted actually to type in all these numbers, but I'll save you from that. Our mean that we had was 63.54. And so our confidence interval is going to be M minus E and M plus E. So it's the mean plus or minus E. And so there's a few different ways that we could write it. We could write the mean as the interval. So our confidence interval we could write as the interval from 61.0608. I'm just going to go to 4 decimal places to 66.0192. Okay, that's one way to write this. Or we could write our confidence interval as 63.54 plus or minus our standard error, which we said was 2.4792. Okay, so there's two different ways to write this. Sometimes the book calls for one way over another, but this is generally how we're going to compute. Let me go back and show you the iPad here. But this is generally how we're going to compute the confidence interval. Okay, so this was our 95% confidence interval, or rather for alpha equals 0.05. Okay, so that's how we do this. Now, what I want to do is I want to also do the 99% confidence interval. And our formulas are all going to be the same with one exception. And the exception is that if we change alpha, the thing that's going to change is this z sub alpha over 2 value. And so what we're going to do is we're going to go to our chart, So now let's do a 99% confidence interval. So again, this is with alpha with a significance of 0.01. We know that n is 10, so just like before, we know n is 10, sigma is 4, our mean was 63.54. And then what we have to do is come up with our z sub alpha over 2. Now, if we take this alpha and divide it by 2, we're going to get z sub 0.005. And it turns out if we go to the table and look up that value, what we're going to get is 2.576. And so we're going to take all this, plug it into R, and we're going to end up with a confidence interval, which is going to be 63.54 plus or minus our standard error, where our standard error was 2.576 times 4 over square root of 10. And that's going to be 63.54 plus or minus our standard error. Our standard error is going to be 2.576 times 4 divided by square root of 10. So it's 3.2584. 2584. Or if I wanted to, we could write it as an interval, and so we could write it as m minus that and our mean plus that, which is going to be 60 point. So we could also write our interval as an interval, and that would be 60.28159, 28159, all the way to 66.7984. Okay, and so that's how this is going to work. Now, I want to emphasize what's happened here. Okay, so I want to emphasize the difference between the 99% confidence interval and the 95% confidence interval. So our 95% confidence interval was centered at the mean. So imagine we have the number line here, and we have our mean 63.54. We can talk about going all the way down to 61.0608. So our 95% confidence interval, let's do that in red. So that goes all the way from 61.0608 all the way up to 66.0192, if I got that right, yeah. And then our 99% confidence interval, let's do that in a different color, say purple. Our 99% confidence interval went from 60.28, so that's a little bit farther. This is not to scale, but emphasizes the point. 60.2816, I should have called that, all the way up to, let me write these values above the number line so they're a little easier to read, all the way up to 66.7984. Okay, and if I'm going to draw them above the axis, I can make these a little bit more accurate. All right. So something like that. So notice that the 99% confidence interval is wider than the 95% confidence interval. Okay, so this is the 99%, the red is the 95%, and so that should make sense if we think about how to interpret the confidence interval. If we want 99% of the samples to have a mean that lies in some interval, it needs to be bigger than the confidence interval if we want only 95% of the samples to lie in that interval, right? If we want to be more confident that the means are going to lie in some interval, we need a bigger interval, okay? And so kind of paradoxically, increasing the confidence decreases the accuracy, right? And to say it differently, if we increase our confidence, we are increasing our error, okay, where the error is this term afterwards, right? So the larger our confidence, the larger the error, which seems slightly backwards until we realize that confidence intervals really are just talking about what percentage of the samples have a mean in this interval. Really, that's all that they're saying. So increasing the confidence increases the error and therefore decreases the accuracy. So if we want to be very accurate, there's a few ways that we can do that. We can increase the sample size until we have a margin of error that's small enough. We could decrease the confidence, but it's kind of a balancing act. Most of the time, you want your samples to have a mean in the confidence interval. Otherwise, I mean, if you have a 50% confidence interval, that's essentially useless. Like half the time, the sample mean is in the interval, half the time it's not. That does not help, right? We need to know most of the time, is it in this interval or not? So oftentimes to kind of walk that fine line, we use a 95% confidence interval. Sometimes a 90 or 95 or 98 or 99. Those are kind of the big threshold values, okay, for confidence intervals. So that is the moral of the story here. Increased accuracy means increased error, and then we'll talk about how to do that. The parting thought for this video, since I've just said it, is we can talk about the error now. The error for a 1 minus alpha confidence interval is going to be given by that extra term. It's the z sub alpha over 2 times sigma over square root of n. Okay, and so that's called the error for the confidence interval. In other words, that's half the length of the interval. That's the length of the interval from the center to one of its endpoints. That distance right there of that red arrow is the error, the margin of error for the 99% confidence interval, and it's for the 99% because that's the one that I went to, the one that was further. So that's the error. And what this means is that if you were to solve for n, you can actually answer the following question. How large does n need to be? So how large does n have to be so that the error is fixed, so that the error is small? And so what we can do is we can completely answer this question now. If we take this formula for the error and solve for n, what that means is that we're going to move the square root of n over, we're going to divide by e, and then we square everything. And it turns out that if we want to have an error of e, what we're going to end up with is this formula. We're going to have z sub alpha over 2, whatever that is, times sigma over e. And since that was for square root of n, we're going to square it. And so whatever this value is, that's going to be how many terms we need to have in order to have a specified margin of error. So if you want a margin of error of only 1%, that's definitely possible if you have enough data. How much data? Well, this amount. So if you plug in z sub alpha over 2 times sigma over e, square it, and then generally this is going to be some non-whole number. So if this turned out to be something like 37.2, you would need at least 38. You would need a sample size of at least 38 to guarantee that you have an error that small. Okay, so this will answer those types of questions for us. And I'll do a few examples again as we go along. Okay, so what we're going to do in the next video is we're going to talk about how does all this work? What do we do if we don't have a good estimate for the population standard deviation? And it turns out that what we have to do is a little bit more complicated than what we have, but not much more at all. And so we'll talk about that in the next video.